So, hello everyone again. This is lecture 3 part 1 of ray optics and optical instruments. In this lecture we will continue the discussion from the applications of total internal reflection, and after that we can go through the reflection through spherical surfaces. First we will go on with the lens makers formula and then we will go to the lens equation. So, let us start the discussion directly. So, I am Samir Lavankar. Let us begin our discussion. So, the course outline for you first of all. So, we started with the introduction in which we understood that two different points are being considered. First is that the ray is the speed of light is 3 into 10 to the power 8 meter per second, and the second is that the ray follows a straight line, that is light follows a straight line. Second thing was that always in this ray optics chapter we are considering light as a discrete particle. So, discrete particle theory is being considered here. Moving to the reflection of light by spherical mirrors concept, in this we understood that first of all we understood the two laws of reflection, that is first is that the angle of incidence is equal to the angle of reflection, and second is that the incident ray, normal ray and reflected ray always lie in the same place. Also before that we also understood the different parameters such as principal axis, focus, pole, etc., the definitions of them. Okay. After this was completed, we understood the third point, that is refraction. So, basically what is refraction? Then the two basic laws of refraction, the first was that the incident ray, normal ray and the refracted ray always lies in the same plane, and the second was known as the Snell's law of refraction, which states that the sine of the angle of incidence to the sine of the angle of refraction is always constant, which is equal to n to 1, which is the refractive index of medium 2 with respect to medium 1. Also we understood the concept that in refraction, what are the applications of refraction, such as one was your apparent depth. Then after this, the third point we understood in the fourth point, that is total internal reflection. So, basically what is total internal reflection? That after a certain angle of incidence, the complete light goes in the same medium only, it does not go in the other medium, the refraction does not happen. So, when the refraction goes 0, the complete reflection happens and the intensity remains intact, then that phenomena is called as total internal reflection. Right now, in the last lecture, in the last few minutes, I explained you the concepts of two applications of total internal reflection. The first was prism, in which there is a bending of light either at 90 degrees or 180 degrees, and the second was optical fibers. Let us continue our discussion from there only, and then we will move on to fifth point, that is reflection at spherical surfaces and by lenses. Okay. So, we were here. So, basically this thing was completed. So, basically one of the example of your what we can say optical fiber was that these are used as light pipe to facilitate visual examination of internal organs like esophagus, stomach and intestine. Okay. Next, you might have seen a commonly available decorative lamp with fine plastic fibers with their free ends forming a fountain like structure. The other ends of the fibers is fixed over an electric lamp. So, basically they are talking about this example here. So, as you can see that it is a decorative lamp with fine plastic fibers. So, these are all nothing but fine plastic fibers with their free ends forming a fountain like structure. As you can see, it is forming a fountain like structure. The other end of the fiber is fixed over the electric lamp. As you can see, it is fixed over the electric lamp. When the lamp is switched on, the light travels from the bottom of each fiber and appears at the tip of its free end as a dot of light. As you can see, dot of lights are visible here. The fibers in such decorative lamps are nothing but optical fibers. So, see, these are nothing but called as, these fibers are nothing but optical fibers. The main requirement in fabricating optical fibers is that there should be very little absorption of light as it travels for long distances inside them. Quite evident, because sometimes it has to be used for kilometers also. So, this has been achieved by purification and special preparation of materials such as quartz. So, basically quartz is used in an optical fiber, and in silica glass fibers it is possible to transmit more than 95% of light over a fiber length of 1 kilometer. So, this is basically much more efficient. So, the things which are used for your transmission of data from using optical fibers is basically the materials used are quartz and silica. So, that is it from the total internal reflection part. Let us move on to new discussion today, that is regarding refraction at spherical surfaces and by lenses. So, let us move on. So, here we have so far considered refraction at a plane interface. So, like we used a plane interface like this, and the incident ray was happening, either it is going towards the normal or it is going or it is going away from the normal. So, basically these two things are being considered. Then also similarly in the glass slab also we considered. So, basically there was a movement some sort of like this. So, every interface was a plane interface every time. Now, we are going to the convex means a curved interface. Now, so let us see what will happen in a curved interface. So, we have so far considered refraction at a plane interface. We shall now consider refraction at a spherical interface between two transparent media. Okay, let us move on. So, an infinitesimal part of a spherical surface can be regarded as planar, and the same laws of refraction can be applied at every point on the surface. Quite evident. Just as for reflection by a spherical mirror, the normal at the point of incidence is perpendicular to the tangent plane to the spherical surface at that point, and therefore passes through its center of curvature. What does it try to say? I will just try to explain to you again. So, let us suppose this is that spherical surface through which the refraction has been taking place. They are just saying, let us suppose this is that incident point, then just first of all make a tangent through it. First of all, just make a tangent through it. So, now if a tangent is being made and a normal is being drawn, then this normal is first of all 90 degrees, and this normal must pass through the center of curvature of the spherical mirror or spherical lens. So, this is the only concept which is being talked about here. So, just as for refraction by spherical mirror, the normal at the point of incidence, just as for reflection by spherical mirror, the normal at the point of incidence is perpendicular to the tangent plane. So, this is the perpendicular to the tangent plane and at that point, and therefore passes through its center of curvature. So, this has to be proved or this has to be regulated. Okay. Next is, now we first consider refraction by a single spherical surface and followed by thin lenses. Okay, so first of all we will consider spherical surfaces first, and then we will move on with the lens concepts. So, what is a thin lens? A thin lens is basically a transparent optical medium bounded by two surfaces, at least one of which should be spherical. Quite evident. So, basically either it can be in this form, either it can be in this form, either it can be in this form, or either it can be in this form. So, this is basically plane surface being talked about on this side of the lens. Okay. Next thing, applying the formula for image formation by a single spherical surface successively at the two surfaces of a lens, we shall obtain the sum called as lens maker's formula and then the lens formula. So, there is no complex formulation to be done. We are just first of all we are deriving the complete concept for one spherical surface, and then using the virtual image formed for the first lens, we are trying to commensurate the second lenses, so the mirror equation for the second lens. Using these two lenses, we can just find out the value of actual image formed by a single lens. So, basically two surfaces are basically comprising of a lens. Now, if we try to use the mirror equation twice, we can find the lens maker's formula and similarly the lens formula. How it is being derived, I will try to explain to you in subsequent slides, but for now, so basically applying the formula for image formation by a single spherical lens successively. So, basically at two surfaces, first for the left surface, second for the right hand surface, we shall obtain the lens maker's formula and then the lens formula. Okay. Next is, so from figure shows the geometry of formation of image I. As you can see, image I is formed of an object O. This is the object O on the principal axis of a spherical surface. Quite evident. This is the spherical surface being talked about with the center of curvature C. This is the center of curvature C and the radius of curvature R. So, anything this can even this can be the radius of curvature R. So, this thing has been completed. Next is, the rays are incident from a medium of refractive index N1 to another of refractive index N2. As you can see, N1 to N2. So, basically there is a refraction happening here. As before, we take the aperture or the literal size of the surface to be very small compared to other distances involved, so that the angle approximation can be made. So, as in the concepts of reflection, we assumed everything to be para-axial. Similarly, here what we are understanding, it is the same concept, only just the method to convey it is being changed. So, as before, we take the aperture or the lateral size of the surface to be small compared to the other distances involved, so that the small angle approximation can be made. So, basically we are assuming that again the same thing has to be occurred here, that is tan theta should be approximately equal to theta, and similarly sin theta should also be approximately equal to theta. This same thing has to be applied here also. Okay. Next is, in particular, Nm will be taken to be nearly equal to the length of perpendicular from the point N on the principal axis. So, same thing is also being applied here. So, basically what they are saying is that Nm, this is Nm, basically this Nm can be taken as equal to the length of the perpendicular from the point N to the principal axis. So, basically we are assuming that this point and this point are very near to each other. Basically we are assuming that the perpendicular from any point on the spherical surface is acting, or is it on the principal axis, touches the point N. What is the point M? Touches the point M. M is basically on the spherical surface. Okay. So, this thing is again the assumption. So, basically as we were deriving it for para-axial for reflection with is assumption that all rays are para-axial. Similarly, we are here deriving same thing, that angle is approximated and can be equal to very small. Okay. Next concept now. So, we have for small angles. So, basically angle NOM. So, what is NOM for you? So, NOM is basically this. So, as you can see, this angle is equal to NM upon OM, quite evident. Next thing is, next triangle is NCM. So, basically NCM is NCM. So, this is your angle NCM. So, this angle NCM is equal to Mn upon MC, Mn, quite evident, as it is Mn upon MC. So, this thing is also clear. And next angle is angle NIM. So, where is NIM for you? This is NIM. So, this is angle NIM for you. So, NIM is nothing but again NM upon your MI. Okay. So, these three things have to be involved for the derivation to take place. So, let us move on slowly. So, now for triangle NOC. So, let us look at the triangle NOC. So, this is the triangle NOC being talked about. In triangle NOC, what is happening? I is the exterior angle, quite evident. So, we have to equate angle of exterior angle with the summation of these two angles. So, basically angle I is nothing but angle NOM. So, basically this angle is angle NOM 1, and next is angle NCM. So, basically this 2. So, a basic concept of mathematics has been used here, that the exterior angle is equal to sum of the opposite interior angles. Okay. Therefore, now just substituting the value. So, NOM is here. So, NOM is being used here, and next was NCM, again NCM is being used here. So, basically it is Mn upon OM plus Mn upon NC. Now, similarly what we can do for refraction. So, basically what is refraction here? Refraction is this portion. Now, this refraction is equal to angle NCM minus angle NIM. So, basically this thing has been explained here. So, basically we are just subtracting two different angles to find out the value of refraction. So, just substituting again value. So, it is nothing but NCM is given to you as Mn upon MC minus NIM is given to you as nothing but Mn upon Mi. So, just substituting these two equations here. So, we are getting angle I and angle R. Now, from Snell's law of refraction, because refraction is happening, this angle R is not angle of reflection, it is angle of refraction. Therefore, from Snell's law we can find out N1 sin I is equal to N2 sin R. So, because we know the refractive index for different media, so we can directly use, we won't use N12 here, we will use N1 sin I is equal to N2 sin R. Okay. So, just substituting the value. So, as we know that the assumption being explained here is that theta is very small. Therefore, we can put the assumption that sin I is approximately, or any sin theta is approximately equal to tan theta is approximately equal to theta. Therefore, we can directly use the formula that N1I is equal to N2R. So, I directly use the formula this derived from this portion here. Now, substituting I and R from the above equation gives you this. So, I am just deriving this again for you. So, basically N1 into I. So, I is basically so M and Mn gets cancelled. Next thing is your N1 upon OM plus N1 upon MC is equal to N2 upon MC minus N2 upon Mi. Now, just some mathematical redistribution gives you n1 upon OM plus n2 upon Mi equal to n2 minus n1 upon MC. So, this is the same equation which is being derived here. Let us move on. So, now here OM, Mi and MC represent the magnitudes of distances, quite evident. So, now applying the sign convention, we can get OM is equal to minus U, OM is equal to minus U, Mi is equal to plus V, Mi is equal to plus V, and MC is equal to R. So, now as you can clearly see that please see the direction of incidence of light was in this direction, but we are measuring the distance OM in the negative direction of this. Therefore, the sign of minus U was used. Now, in the same way the direction of incidence was in this way, and we are measuring the distance Mi from this portion in this direction. Therefore, the value of plus V was used. Similarly, for MC value, as the direction of incidence of light was in this direction, and we are measuring again in this direction, the value of plus R was used. So, basically this is the basic sign convention which you need to remember. Okay, let us move on. So, substituting these values in the above equation will give you n2 by V. So, basically what is happening here? So, n2 by OM, OM is nothing but minus U. So, n2 by, let me just first of all write the equation again. So, n2 by OM, sorry, n1 by OM, n1 by OM plus n2 by Mi is equal to n2 minus n1 by MC. So, n1 by OM plus n2 by Mi is equal to n2 minus n1 by MC. So, let us substitute the equation now. So, n1 by OM is your minus U plus n2 by Mi is your plus V equal to n2 minus n1 by MC, MC is your plus R. Therefore, just substituting, just iterating it as equation is given. So, n2 minus n2 by V minus n1 by U is equal to n2 minus n1 by R. So, this is the equation which is being formed here. Now, this equation gives us a relation between the object and the image distance in terms of refractive index of the medium and the radius of curvature of the curved spherical surface. So, basically you already know the value of n2 and n1, you know the value of U, you know the value of capital R, you can directly find out the value of capital V, that is the image distance. Where will the image formed? Image will be formed on the second side, that is on the right hand side of the mirror. Let us assuming that the incidence is happening from the left hand side to the right hand side. Okay, it holds for any curved spherical surface. It holds for any curved spherical surface. Okay, so the conclusion of this lecture only, let me stop it here only. So, the conclusion of this lecture is we found a equation which is equal to n2 by V minus n1 by U is equal to n2 minus n1 by R. This can be used. This is a basic refraction, basic concept of refraction are being involved, and a relation has been found between U, V, and R. Okay. So, it holds, so basically it is very important, it holds for any curved spherical surface. So, basically does not depend, it is either concave or convex, it holds for any spherical surface. Okay. So, let me stop it here only, I will continue discussion from this portion in the next class. So, thank you so much.